Imagine rolling a ball toward a solid wall. What happens? The ball hits the wall and bounces back, just as you'd expect. It can't go through the wall because it doesn't have enough energy to break it or climb over it. That's the everyday, classical world we're used to. Now, picture this. In the quantum world, if that ball were a particle, like an electron, there's a tiny chance it wouldn't bounce back. Instead, it would vanish on one side of the wall and reappear on the other side. No breaking, no climbing, just passing through. Sounds impossible, right? But this isn't science fiction. It's a real phenomenon called quantum tunneling, and it defies everything we think we know about how the world works. Please stay with us as always. To wrap our heads around this, we need to leave behind the rules of the classical world and dive into the strange world of quantum mechanics. Particles aren't just tiny dots. They behave like waves. And these waves have a chance of penetrating through barriers. To make this clearer, let's explore 3 everyday analogies that show how quantum tunneling works. Imagine standing at the base of a tall mountain. Climbing over it requires a lot of energy, effort, and time. But what if there's a tunnel that goes straight through the mountain? You could walk to the other side without climbing at all. In quantum mechanics, the barrier is like the mountain, and tunneling is the shortcut that lets particles get to the other side without using energy to climb. Here's another way to think about it. Picture a ghost standing outside a locked room. Normally, a solid door would block someone from entering. But since the ghost can phase through walls, it just slides right through and appears inside. In the quantum world, particles can act like this ghost. Even though the barrier should block them, they sometimes phase through, thanks to the weirdness of quantum mechanics. Or imagine a dam holding back water. The wall is solid, and most of the water stays behind it. But a small trickle of water might seep through cracks in the dam. In a similar way, when a quantum particle approaches a barrier, a tiny part of its probability wave seeps through to the other side, and that's enough for the particle to make it through. These analogies help us imagine tunneling, but what's really happening is even stranger. Particles like electrons don't just behave like tiny marbles. They also act like waves of probability. And in this quantum wave-like state, they can leak through barriers. Now that we've seen the big picture, let's dive deeper into how this works and why it's not just a scientific curiosity. It's a fundamental part of the universe. Quantum tunneling is one of the strangest phenomena in physics. In simple terms, it's when a particle, like an electron, goes through a barrier it shouldn't be able to cross. Imagine you're standing in front of a high wall. In the classical world, the world we experience, you'd need to climb over it or break it down to get to the other side. But in the quantum world, you could just appear on the other side. No climbing, no breaking, just poof. Magic, right? Not quite. It's quantum mechanics. To understand tunneling, let's first talk about energy. Normally, for a particle to cross a barrier, it needs enough energy to climb over it. If it doesn't have enough, it's stuck. But here's where quantum mechanics breaks the rules. In the quantum world, particles don't behave like tiny balls. They also act like waves. These waves spread out, and part of them can leak through a barrier. This leaking means there's a small chance the particle can appear on the other side, even though it doesn't have enough energy to cross the barrier. This is quantum tunneling. You might be wondering, why do particles behave like waves? This is because of something called wave-particle duality. In quantum mechanics, particles like electrons aren't just tiny dots. They're also described as waves of probability. This wave tells us where the particle might be, and if the wave reaches the other side of the barrier, the particle has a chance of showing up there too. It's like rolling a dice with quantum rules. Even the seemingly impossible has a probability. Now you might be thinking, this is cool, but where does it actually happen? Great question. First, let's talk about nuclear fusion, the process that powers the sun. Inside the sun, particles like protons shouldn't have enough energy to overcome their natural repulsion and fuse together. But thanks to quantum tunneling, they do. This allows stars to shine and life to exist. Another example? Your everyday electronics. Quantum tunneling is the key behind devices like the scanning tunneling microscope, which lets us see individual atoms. It's also critical in modern computing and semiconductors. Quantum tunneling isn't just a bizarre party trick of physics. It's a gateway to understanding the universe on the deepest level. Let's pause for a moment and think about the scale of its influence. At the tiniest level, tunneling is what allows particles to interact and create the building blocks of matter. Without it, the sun wouldn't burn, atoms wouldn't form, and the chemistry of life as we know it would be impossible. It's not just a strange quirk, it's a fundamental thread in the fabric of existence. Think about that for a second. Every beam of sunlight that warms your face exists because of quantum tunneling. The light from distant stars, the energy that drives ecosystems, all of it hinges on this microscopic phenomenon. But the impact of tunneling goes beyond what we can see and use. It challenges our very understanding of reality. It forces us to rethink the limits of what's possible. In the classical world, barriers are obstacles, but in the quantum world, they're just suggestions. This opens up fascinating possibilities for the future. Could quantum tunneling one day help us develop technologies like teleportation or quantum computers that outperform today's most powerful machines? Could it lead to breakthroughs in energy, medicine, or even interstellar travel? The truth is, we're only scratching the surface of what tunneling and quantum mechanics as a whole can teach us. And that's the beauty of science. It takes the impossible and makes it real. The journey has only just begun, and with every discovery, we move closer to understanding the ultimate questions of existence.